Now we can start.
Thank you. Let us start. We are going to prove the classification theorem for spherical varieties, which I formulated at the end of the previous lecture and which I recall now. The theorem says that spherical varieties with a given open orbit, a spherical homogeneous space Y0, are in a one-to-one correspondence up to an isomorphism with colored fans in the vector space E spanned by the dual of the weight lattice, or Y0. And the correspondence is given by associating to each spherical variety X its colored fan, f of X, which is just the collection of colored cones corresponding to all G orbits in X. We have already proved at the previous lecture that this collection of colored cones is indeed a colored fan. That is, it is closed under taking colored faces, and any two cones from this collection, the interiors do not intersect inside the valuation cone. This is the definition of the colored fan, and we have proved by lemmas from the second one to the fourth one, lemmas 2, 3, 4, at the previous lecture, that the collection of colored cones associated with X satisfies the definition of the colored fan. Now we want to prove that this correspondence is bijective. So let me turn to the proof of the theorem. Let's first prove the injectivity of the correspondence. So suppose we have two spherical varieties, say X and X prime, with one and the same colored fan. F of X coincides with F of X prime. And let me enumerate the colored cones in this fan by some index I. So the colored cones are Ci, comma Bi, where Ci is a pointed cone in the vector space E, and such that its relative interior intersects the valuation cone, and Bi is a certain subset of colors. So the index I, let it range from 0 to some big N. Okay, so what does it mean? This means, in particular, that the variety X is decomposed in a disjoint union of as many G orbits as there are many colored cones in this fan. So the orbits Y sub I are also enumerated from 0 to N. And so these are G orbits. Let me write it somewhere here. So I will put it somewhat below. Okay, let me put it here. So these Yi's are G orbits. All G orbits in X. And equally, we can decompose I as a union, no longer G-joint, of course, as a union of simple open subvarieties Xi over the same set of indices, where Xi is a simple open subvariety corresponding to the orbit Y sub I. So xi is the union of all orbits containing this one y sub I in the closure. Okay. For each of these orbits y sub I, and for each of these simple open subvarieties, the respective colored cone, say C sub yi, comma d over yi, is precisely this one, is equal to C sub I, B sub I. Okay? And absolutely similarly, we have a similar decomposition for x prime, because the fan of x prime is the same by assumption. So let me write this decomposition below. So x prime is also a union of the same number of orbits. Now let me denote them by y sub I prime, or equivalently, it is the union of simple embeddings xi prime where this xi prime is the same as x sub yi prime. It consists of all simple, it consists of all orbits. It is the union of all orbits whose closure contains y sub I. Okay.
What closure contains y sub I?
So what is what is this notation?
This notation is a set of points that the closure of the orbits contain y I. I know that.
Exactly. So yes. So this is the definition of this guy. So the union of all orbits whose closure contains this given orbit yi prime. Okay. And the cone, the colored cone corresponding to each of these orbits is the same one. So let me maybe add this here. Let me shift a little bit to take. Yeah, so let me write first. Let me write that the colored cone is the same for this orbit. Okay, now I will move it a little bit to the left for convenience. Yeah, let me put it here. Okay, just a moment, excuse me. I will turn off my microphone for a while. Excuse me for the interruption. So we have this picture, okay? And now recall that we have a theorem on classification of simple spherical varieties, which says that a simple spherical variety containing a given open orbit y0 is uniquely determined by its colored cone. This means, so each of these simple spherical varieties xi and xi prime contains y0 as an open orbit. So y0 here and y0 here are open orbits. And the theorem which I just quoted says that the identity map on this open orbit extends uniquely to an isomorphism, to a G-equivariant isomorphism from this variety to this one. So there is a unique isomorphism extending the identity map on the open orbit. We get that we have an open cover. Of X with these Xi's and an open cover of X prime with Xi primes, such that the identity map on the open orbit extends to isomorphisms between these subvarieties giving these open covers. And since this holds for each I, we get an all these isomorphisms glued together to an isomorphism from X to X prime. So finally, we get from this an isomorphism from X to X prime. So we have proved that if two spherical varieties have one and the same colored fan, then they are isomorphic. They are G-equivariantly isomorphic. Essentially, this stems from the isomorphism from the classification of simple spherical varieties. Okay. Now let's turn to the surjectivity of this correspondence. So surjectivity. We have to prove that for each colored fan, there exists a spherical variety X, whose colored fan is the given one. So suppose we are given a colored fan. Let F be some colored fan. I will use the same notation for the colored cones in it. So the colored fan F consists from colored cones C sub I, B sub I, where I ranges in a finite set of numbers from 0 to some n. So suppose it is a colored fan. And so we choose the numbering of these cones in such a way that the number 0 corresponds to the smallest cone in this fan. So we suppose, just by choosing the numbering, that C0, B0 is the smallest cone in the colored fan, consisting of the 0 cone and the empty set of colors. This colored cone corresponds to a simple spherical variety, which is just the homogeneous variety. Why not? Okay. Now, for any of these cones,
well, they are equal, or just isomorphic in some sense.
No, just equal, just equal. Because what you see, one of the conditions defining the colored fan is that this set is closed under taking colored faces. But if you take any colored cone, you can take the smallest colored face it contains. It is just the vertex, the apex that is the zero vector, the cone consisting just from zero, and the empty set of colors. Such smallest face is contained in any colored cone. And also we know that this colored cone, by the example from the previous lecture, we know that this colored cone corresponds to the homogeneous variety itself.
To I naught. Yeah.
Yes, to Y naught, exactly. Now, for any cone, for any colored cone in this colored fan, let us take the respective simple spherical variety xi. This is possible by the classification theorem for simple spherical varieties. Simple spherical variety with the open orbit Y naught. So we have finitely many simple spherical varieties with one and the same open orbit corresponding to the colored cones in the given fan. Okay? Excuse me, just one moment, please. I'm sorry. I have to turn off my microphone for a while. Yeah, excuse me. Let's continue. So we have this finitely many simple spherical varieties. And now for any pair of indices, I and j, we have a unique G-equivariant birational isomorphism from xi to xj. So let me write this. For any I and j, we have a unique birational isomorphism from xi to xj, extending the identity map on the open orbit. So let me denote this isomorphism by phi I j, okay? Birational isomorphism. And we may consider the maximal open subsets in xi and xj, respectively, for which this birational isomorphism becomes a biregular isomorphism. So let me denote by xij here and xji here. xji. The biregularity loci for this map phi ij. So the biggest open subsets such that phi ij is an isomorphism between these subsets. For instance, each of these open subsets contains the open orbit, Y naught. Because for Y naught, it is just the identity map from this Y naught to this Y naught, okay? Actually, these subsets can be described combinatorially. The colored fans of these open subvarieties are just the sets of colored faces which the two colored cones, CIBI and CJBJ, have in common. So these colored cones are different, but they may have common faces. And these faces correspond to open simple subvarieties in here and in here. So if these faces coincide for I and for j, then the subvarieties are isomorphic. And the union of all these subvarieties is the biregularity locus for this map. Okay? In fact, these subvarieties xij and xji are even simple. So let me leave it as an exercise for you. Somewhere here. Exercise 1. Prove that xij and xji are simple spherical varieties. Are also simple.
The condition for the proof is that they are the largest biregularity.
Exactly. The largest biregular isomorphic open subsets in here and in here. Yeah. So we have the following picture. Maybe I can draw this picture here. So we have xi, one simple spherical variety. We have xj, another one, and some pieces. Yeah,
Professor.
Yeah.
Why should they be simple?
This is an exercise. This is an exercise for you.
I think due to your statement means that the intersection not the intersection the intersection I don't mean intersection, I mean xij and xji correspond to the intersection of ci bi and cj b, the intersection of ci bi and cj bj. But
well. I mean, I don't want to discuss this exercise now. Just try to prove it. It is not difficult in view of the correspondence between orbits contained one in the closure of another one and colored faces and all this stuff, which we discussed on the previous lecture. But try to prove it. So if you will have some more questions, if something will be unclear, then we can discuss it later. But so far, let me leave it just as an exercise. I won't use it. I won't use this exercise for the proof. And that's why it is an exercise. That's why I don't explain it now. It is not needed for the proof that they are simple, but this is the case, okay? Let me describe the picture. So we have xi and xj. We have two different simple spherical varieties containing the open orbit y0, but some pieces of these varieties are isomorphic. So we have xij here. We have xij here. Let me paint it in blue. So to make it visible clearly. So we have xij here. And similarly, we have xji here, xji here. Again, I'll paint them in blue. Like this. And these two pieces are isomorphic under the map phi ij. Excuse me. Now I want it to be black. From here to here. Okay. So we have this picture for each pair of indices xi and xj. Okay? And what we can do now? Now we can glue all these simple spherical varieties xi, where I ranges from 0 to n, glue them together along these isomorphic open subsets. So formally speaking, we have to consider the following. We have to consider the set X, which is just the disjoint union of all xi's modulo some equivalence relation, where the equivalence relation is defined as follows. So a point xi in big Xi is equivalent to a point xj in big Xj if, so as I said, xi belongs to big Xi, xj, well, maybe better to say xi belongs to big Xij, xj belongs to big Xji, to this and these open subsets in here and in here. And these points are related under this map. So phi, so I don't like this notation. Maybe let me change the order of indices. So let me put here fji, the map from xi to xj. Let me denote as xj, phi ji. Phi, I'm sorry for this confusion. Let it be phi ji from here to here and also here, of course. So like let me do it like this. Yeah, this will be more symmetric. So this map phi ji sends xi to xj. This is exactly the formal definition of what I called gluing these xi's along these open subsets. So gluing xi with xj along these open subsets. So this gives an equivalence relation on the disjoint union of xi's, and gluing all these guys together, we obtain an algebraic variety X, such that these xi's are open subset in X, but now they are intersecting. Yeah.
The gluing is I think we should prove the well-definity of the gluing, because I mean different xij, for example, if a point in xij and in xkj are pasted to the same point in xj, we should check that the 2 points in xi and xk is also related by some phi.
Yeah. You are right. Of course, we have so to be rigorous, we have to check all these things. But this is not difficult, because so the main point here is that for any two of the varieties under consideration, so if they are isomorphic, for any two varieties under consideration, there is a unique isomorphism between them, extending the identity map on the open orbit. And if we have the third one, say xjk or something like this, again, it is isomorphic to this one. Well, maybe on a smaller open subset, it is isomorphic to another one. A smaller open subset in here is isomorphic to an open subset in some xk. and we get an isomorphism from here to here for, again, for some smaller open subsets. But this isomorphism uniquely extends the identity map here. So it is the same isomorphism as it should be for the pair of indices I and K. Something like this. So the transitivity of...
I know. So we use the uniqueness to prove.
Yeah. So for transitivity, you use that this identity map uniquely extends to an isomorphism. This is a good remark. It is good that you follow the argument, but this is not difficult. I just skip it because because it is just general things about extension from open subsets in Zariski topology. Open subsets are dense and so on. Okay. So we have this big variety X equipped with the action of G, such that each of the Xi's is an affine G is an open G stable subset in X, and by construction we have that the fan of X is equal to the initial one which we started with. This is just by construction. The only thing we have to prove is that the variety X is separated. Well, we can say that we have to prove that the variety X is the variety, a true algebraic variety in our sense, because some time ago we agreed to consider only separated algebraic varieties. In this language,
I think we should check the normality of X.
Well, normality is easy because it has an open. Normality is easy because it has an open covering.
It is covered by normal varieties.
Yeah, it is covered by open normal varieties.
Normal. When we talk about normal, we did not require a separability.
Well, formally speaking, we may not require separability, but anyway, we have to prove separability. This is what we are going to prove. So, because we want to consider only separated algebraic varieties, and this guy which we constructed, this X, a priori may be non-separated. So, in the other terminology, it is not an algebraic variety; it is a pre-variety. So sometimes non-separated algebraic varieties are called pre-varieties, and varieties are assumed to be separated pre-varieties. This is another terminology which I didn't use, but anyway. So far we constructed a pre-variety, and we have to prove that it is a true algebraic variety. That is, it is separated. It is the only thing left to prove. And let's do it. So separation property. Well, separation property says that the diagonal is closed, that the diagonal is closed in the double of X. In X cross X. But since this pre-variety X, which we constructed, is covered by open subsets Xi's, the product X cross X is covered by open subsets Xi cross Xj. And it suffices to prove. It suffices to prove that the intersection of this diagonal with each of these open subsets Xi cross Xj is closed in this open subset. But this intersection of the diagonal of X with Xi cross Xj under our identification, so Xi and Xj are glued exactly along these two subsets Xij isomorphic to Xji. So it suffices to prove that Xij diagonally embedded is closed in Xi cross Xj for any I and j.
why we only need this to?
Well, because these guys, these open subsets cover the whole x cross x, and if you intersect this diagonal with xi cross xj, you obtain this, because xi cross xj are glued exactly along this set.
So the diagonal. Well, you are using that the diagonal intersecting and an open cover closely, then the diagonal is closed.
Exactly.
How can we prove this?
Well, this is just a general topological argument. If you have a subset whose intersection, with each of the open covering sets is closed, then the subset is closed. Just an exercise in topology, in general topology. Basic properties of closed and open sets. Okay, if it is not absolutely clear, let me leave it as an exercise to you, but this is just very elementary topological thing. So closedness is a local property. If you have an open cover such that the intersection with each subset in its open cover is closed, then the whole set is closed. Okay, so it suffices to prove this, and even we may assume that I is non-equal to j. Because if I is equal to j, then this is trivial. Xi is the same thing as j, and the diagonal in xi cross xi is closed because xi is quasi-projective. It is separated in particular. So it suffices to prove these things for distinct indices I and j. Well, let me maybe try to draw the picture for this situation. So let me put, excuse me, let me put, so I'm trying to draw the product of xi and xj. So this will be my xi, this will be my xj, this is the product variety. Okay, so let me write that this is xi. The horizontal thing is xi. The vertical thing is xj. We have a product variety. And in this product variety, we have xij and xji. Let me put it in blue. So this will be say xij. This will be xji. And suppose we know that they are isomorphic. The picture is like this. So this is xij. This is xji. Let me draw the diagonal. Diagonal of xij. This is this. Yeah. This is the diagonal. And we want to prove that it is closed, not just in here, but in the whole product in here. Well, suppose we argue by contradiction. Suppose it is not the case. Suppose that the diagonal of xij is not closed. So the closure of this diagonal minus the diagonal itself is non-empty. Of course, all these varieties, all these pre-varieties, varieties, whatever, are G-stable, stable under the action of G. So Xij is G-stable, the diagonal of Xij is G-stable, its closure is G-stable, and the boundary set, the complement of the diagonal in its closure, is also G-stable. And if it is non-empty, then it contains some G orbit, say Y. So Y is a G orbit in this boundary set. G orbit. Let me try to draw it somewhere here. Well, maybe like this. So we have some Y here, some orbit in the closure of the diagonal, but not belonging to this blue square. This is Y. Now, by properties of elementary embeddings, which we discussed previously, we can say that there exists a vector in the valuation column V such that there is a morphism from the respective elementary embedding of xv of x, the variety xv, to this closure of the diagonal, because it is this closure, so it is still a spherical variety containing y not as the open orbit. It may be non-normal, but then you can normalize it. It is not a problem. And if you have an orbit in here, you can blow up this orbit. We already used this construction several times, so you can blow up this orbit and obtain an elementary embedding whose boundary divisor dv maps exactly to this orbit. Okay, so you have this picture. Now let's consider the projection. Let's consider the projection of this closed diagonal of this guy to xi and to xj. So we have two projections to here and to here. Projections. And under these projections, the orbit y maps to some orbits, say yi here, and yj here. Okay. Again, I try to draw these orbits. So yi is something here. The projection of y. And yj is something here. We may even assume that these orbits yi and yj are closed in xi and xj respectively, because otherwise we can just replace xi and xj by a smaller simple open subvariety. We can take only those orbits in xi which contain yi in their closure. So replacing xi and xj with simple open subvarieties, we may assume that yi is closed in xi and yj is closed in xj. But then again, by the properties of elementary embeddings and morphisms from elementary embeddings to spherical varieties. So now we consider the morphism from xv to here, the composite of these two, and the morphism from xv to here, the composite of these two. And we have that the boundary divisor of this elementary simple variety, the boundary divisor dv, maps here onto this orbit, and here it maps onto this orbit. By properties of elementary embeddings, we get, which we discussed at the previous lecture, we get that the vector v defining this elementary embedding belongs to the relative interiors of both cones, Ci relative interior and Cj relative interior. And also it is a vector in the valuation cone, so it belongs to this intersection. But this is a contradiction because one of the properties, so this is a contradiction. Because one of the properties of the colored fan is that the relative interiors of distinct colored cones do not intersect inside the valuation cone. So this intersection should be empty. So this contradiction with our initial assumption that we have something on the boundary, that the boundary of the diagonal is non-empty, this contradiction with this, let me stress, we get contradiction with this assumption. So this contradiction proves that actually the diagonal is closed in each of these cross products, and therefore it is closed in x cross x, and finally we get that x is separated. So this ends the proof of the theorem. Okay. Any questions? So you see here that the second condition on the colored fan, the condition that relative interiors do not intersect inside the valuation cone, this second condition stands for separation property. This is the geometric meaning of this condition. Well, still no questions?
Sorry, I have a question.
Yes.
So if two colored fan differs from each other by some linear transformation, maybe action of some GLN, such like that, so they correspond to two different varieties.
Yes, because, well, formally speaking, what we do, we are considering, we are classifying not just varieties, we are classifying embeddings of the open orbit y naught into some variety. Because whenever we speak about isomorphisms between two different varieties, we assume that this isomorphism extends the identity map on the open orbit. So we do not want to move points in the open orbits. We only consider such isomorphisms. And under this strict assumption, yes, what you have said gives you a different spherical variety, a different embedding of this y naught. But it may happen that you have an isomorphism between two spherical varieties, which gives you a non-trivial isomorphism of y naught. Then it is possible that one fan is obtained from another one by some linear transformation. It is possible. Of course, not any linear transformation will suit, but sometimes it happens. For instance, in the toric cases, it is quite often. We shall discuss toric case later, but I can say that in the toric case, if you weaken the condition on isomorphism, if you do not require the isomorphism to extend the identity map on the open orbit, then yes, they can be isomorphic.
Okay, thanks.
I have
yes.
questions.
Yes.
Well, the last page, I think.
This one. Oh, sorry, last page. This one. Mm-hmm.
So, why can we shrink xi to be the
Why can we shrink? I understand. Why can you shrink xi? Let us replace xi with the open simple subvariety consisting of all g orbits containing this one in its closure.
Yes, I mean that. I know this.
Then this guy, yeah, I mean,
if we shrink xi, how can we ensure that the closure of diagonal is still contained in the product? I mean this.
Well, if we shrink xi in this way, then of course this will remain. How to say? Yeah, I mean this will remain unchanged. This will remain unchanged. Well, maybe.
Why this will remain unchanged?
No, yes. It may also shrink, but it is harmless because if you had, what we still would have, we would still have that this guy will be in the closure of what is left, because this guy sits in the product of shrinked xi and shrinked xj. Both projections.
We just consider y and not about the other part of the diagonal, right? And
yes. We forget about the whole closure. We forget about the whole closure, and we contain only. We look at the part of this closure which contains y. Yes. So so the claim is that when you shrink xi and xj in this way, then still this diagonal, this set may be smaller, but still this diagonal will be non-closed, and the closure will contain this orbit. Because both projections of this orbit on here and on here will be preserved. We do not kick them out. Okay? Okay. So, by the way, we have finished the first half of my lecture, so now it's break time. And still you may ask questions if you have questions, but now we are on the break. We have 8 minutes of the break left, as I see on my watch. So please ask your questions if you have any. And if not, I will just switch off my microphone and switch it on again, should you have any questions.
Professor.
Yes, I'm here.
Well, and I was looking at my note.
Okay.
why should we have v in the relative interior? I mean,
Well, we have proved, yes, indeed you have to look at your notes, because we have proved, I guess, on the previous lecture, that if you have a map from an elementary embedding to some spherical variety such that the boundary...
Well, I don't think this is an embedding. It's just a map.
Well, this guy is called, no, this map is not an embedding. I mean, this guy, xv, is an elementary embedding of y0. This
yes.
xv contains y0 as the open orbit. This, in this sense, I mean, this guy is an elementary embedding, or let me call it an elementary variety. Just not to get confused with this word, embedding, let me call it elementary variety. So if we have a map from an elementary variety to a simple variety xi such that the boundary divisor maps to the closed orbit. In this case, the vector v defining this embedding belongs to the relative interior of the cone corresponding to this simple variety. This we have proved. This was a remark. I guess this was a remark in the proof of lemma 3. I think so. Yes. I can try to open the notes of the previous lecture and even show you. Yeah, I mean this one. I think you see this statement. So if the boundary divisor maps to some orbit y prime, then this vector v belongs to the relative interior of the respective cone. Okay?
I see.
Okay. Well, Let's proceed with the lecture. So we have finally obtained the classification of spherical varieties in terms of this combinatorial or geometric, whatever you call it, this data called colored fans. But actually, we've got much more, because the structure of this data, which we used for classification, allows us also to study the geometry of spherical varieties. And the first geometric consequence is immediate from the properties of colored fans. It describes the mutual position of orbits on a spherical variety, namely the closure ordering of orbits. So the closure ordering on orbits is described in the following way. We have that in the previous notation, we have that one orbit y sub I is contained in the closure of another one, y sub j, if and only if the colored cone associated with the bigger orbit, Cj, Bj, is a colored face of the colored cone associated with the smaller orbit, Ci, Bi. This actually was proved in the previous lecture, because we described colored faces of the colored we described colored faces of this colored cone corresponding to this orbit exactly as the colored cones corresponding to bigger orbits on the same simple variety xi containing this one in their closures. So there is nothing to prove here because it is already proven before. But this gives you a clear picture of how all orbits on a spherical varieties are mutually positioned with respect to each other. The closure ordering on them is exactly the reverse to the ordering or to the inclusion ordering on faces on cones in the colored fan, because each colored face in the colored fan is still a cone belonging to the same colored fan. So associating with a G orbit a colored cone reverses the ordering. So the bigger is the orbit, the smaller is the cone. Okay? This is the first geometric consequence of our considerations. And now we establish a criterion of completeness for spherical varieties in terms of their fans. So the next theorem is a criterion of completeness. Theorem 2. The criterion is actually very simple. A spherical variety X is complete if and only if its colored fan covers the whole valuation cone. Well, when I say that a fan covers some set, I mean that the union of all cones, in this fan, the union of all these CIs contains this valuation cone. So a very simple description, which we have for completeness. Let's prove it. So we have to prove the implications in two directions. So from the left to the right and reverse one. Let's start with this implication.
What do you mean by cover? Do we need both covering, which means CI should cover Vy and Bi should
Well,
cover all.
let me repeat exactly what do I mean. I said it in words, but let me write it now, since the question arises. This means exactly that the union of all cones in this fan over all g orbits in X contains, maybe is equal, contains the evaluation cone. This is exactly what I mean by covers. Okay? So let's proceed with the proof of this direction. So suppose X is complete. And suppose that the fan of X does not cover the evaluation cone. This means, so suppose this means that there exists a vector in the evaluation cone which does not belong to the union of cones corresponding to g orbits in X, to the union of cones in the fan. Well, something like this. Let me draw a picture again. So you have the fan consisting of cones and their faces and so on. Let me draw a fan for you, some fan. For instance, this cone. Well, maybe let me use a different color. This cone, this cone, this cone, and so on. So these are cones in the fan. Let me maybe paint them in some colors. This is the first cone. Just to distinguish them. These are just cones in my fan. And of course, all faces, all colored faces of these cones should be also included in the fan. Maybe this one. Also. And this one. This is my fan. And suppose I have a vector in the evaluation cone. Let me mark it in green. This vector V. Which does not belong to the union of all these cones, like this. Then I can increase my fan. I can consider a bigger fan. Let me denote by F prime. By F prime, let me denote a fan which is obtained from f of x, from the fan of x, by adding a single colored cone, which is just a ray generated by this vector v. With empty set of colors. Like this. Well, maybe I will again move it slightly to the bottom. Okay. So I add array. Maybe I will just put it here. I add array to my initial fan, array spanned by this vector. Okay. Then it is clear that this set is still a colored fan. So it is still closed under taking faces, because the only face of the cone which I add is this zero cone, this one. Yeah, but the zero face was also was already present in this fan. This zero face was already here, so this set is still closed under taking faces. And again, the relative interiors of the cones do not intersect because of this condition. Because of this condition, so we get a colored fan, a bigger colored fan. And geometrically, this means that this fan, it follows from the classification theorem, that this fan corresponds to a spherical variety X prime, which is bigger than X. Actually, X prime is a union of X and the elementary variety corresponding to this vector V. These two are open subsets. Both X and XV are open subsets in X prime, because their fans are parts of the fan of X prime. So these are open subsets. So that the complement of X in X prime, what is missing in X to get X prime is exactly the orbit corresponding to this ray, the boundary divisor. Okay, but this means that X is not complete. Because we extended it, we embedded it as an open subset in a big variety. This means that X is not complete. And this is a contradiction with our assumption. So we proved that if X is complete, then its fan covers the whole valuation cone. Okay. Now let's turn to the reverse implication. If the fan covers the valuation cone, then the variety is complete. So we argue in the following way. First, we may cover my X by open simple subvarieties, Xi's, where Xi's are open and simple spherical subvarieties. And also we know that each simple spherical variety is quasi-projective. Simple implies quasi-projective. And since each Xi is quasi-projective, we may embed it in a projective spherical variety as an open subset, as an open G-stable subset. So we may consider the projective closure of each Xi in some projective space, in some ambient projective space. Xi bar, so these are open embeddings. and xi bars are projective spherical varieties. Okay. Now we have a rational map. Again, extending the identity map on the open orbit, we have a rational map from X to each of xi bars, extending the identity map on the open orbit. And therefore, we have a rational map to the product of all xi bars. Let me denote this map by phi. This product is a projective variety. And we may consider the closure of the image of this map in this projective variety. Let it be x prime. The closure of the image of this rational map. Now we have yet another rational map from X to X cross X prime. Another rational map. Excuse me, let me maybe move it to here. One line below. This map, say big phi, is just a product of two maps, the identity on X and small phi from X to X prime. So we get this diagonal map, rational map from X to X cross X prime. And as similarly as before, we consider the closure of the image of this map. Let it be X double prime. So that we have two projection maps from X double prime on one side to X, and on the other side to X prime. And also for each, excuse me, for each of i's, for each of these indices I, we have a projection map from X prime to xi bar. We have this projection map from xi, from X prime to xi bar, which I denote as pi. And by the way, this map I will denote as p, and this map will be p prime. So this is my picture, and again, let me draw a true picture for you of all this stuff. So the picture will be like this. So you have this product variety X cross X prime. So let it be somewhere here maybe. X cross X prime. This will be my product variety. I'll put X here. And X prime here. And also I have projections from X prime to each of xi bars. So let me indicate xi bar somewhere here. Well, maybe here. Let it be here. This will be xi bar for some I. And we have this map. We have the map pi sub I, the projection map from here to here. And also we have x double prime, which is the closure of the image of this rational map phi from x, from this horizontal line, to x prime, to the vertical line. So x double prime is somewhere here. It's some kind of diagonal. Of course, it is not a true diagonal because these two varieties, x and x prime, are not the same. But it is something like the diagonal. It is the image of this rational map. So let this dashed arrow denote the rational map phi. So that the inverse map, this one, is the projection pi, and this map is the projection pi prime. This is the picture of all things which we consider. Now I claim maybe I will claim it here. I claim that pi prime is an open embedding. Pi prime from x double prime. By the way, this is x double prime. This curve indicates x double prime. And I claim that this projection map pi prime from here to here is an open embedding. In other words, pi prime identifies this variety x double prime with some open subvariety in x prime under this projection map. Let's prove the claim. So we have these projection maps from x prime to xi bars, to these projective varieties, xi bars. And actually x prime is just contained in the product of these varieties. Inside xi bar, we have an open subset xi. And we can consider the inverse image of this open subset under this projection map. So let's denote these subsets by xi prime. Xi prime are the inverse images under pi I of the open subsets xi. These are open subsets in x prime. Let me indicate them in red, for instance. So we have this xi here, and the inverse image of this xi will give you an open subset xi prime. So this will be xi prime. Okay. Now, let's consider the following. So we have that a point, say x double prime, take any point x double prime in big X double prime, say let it be, for instance, this point. x double prime. Then this point has two projections, a projection to x and a projection to x prime. Let's consider first the projection to x and denote it by x without primes. So this x, which is pi of x double prime, is a point in the variety x. But the variety x is covered by open subsets xi, and therefore this point belongs to some of these open subsets. So x belongs to xi for some I. Okay? This means that actually x double prime is a pair of x and some point x prime. X prime is this point, of course. X prime is this point. Where this point x prime has a property, has a property that its projection on the pi I, so pi I of x prime equals to x. So the projection of x prime under this map pi I, under this projection, we get the same point x as here. So the picture is exactly like this. This is because this identity, this equality, pi I of x prime equals to x, where x prime and x are two projections of x double prime onto to big X and to big X prime. So in this notation, if x and x prime are two projections of x double prime, then this identity holds identically on the inverse image of xi under the projection pi. So let me write it here. So this holds identically on pi inverse of xi. So let me do it with more space. Identical. This holds identically on the inverse image of xi under pi. So here on the picture, I can draw xi also here. Well, somewhere here. Let it be xi here in x. And if I take the inverse image of xi under the map pi, the inverse image in x double prime, so this is this open set from here to here. On this open set, this is an identical equality. because this holds over the open orbit. So if the point x belongs to the open orbit, why not? Then all these maps are just diagonal maps. This map phi, this birational map phi on the open orbit is just the diagonal map. It sends a point to a tuple of the same point multiplied several times in this variety. And this is also a diagonal map. And for the diagonal map, of course, the projections are equal. If you have the image, something in the image of the diagonal map, then these projections are equal. So this holds on the open orbit. But x double prime is the closure of the open orbit. So if some equation holds on the open orbit, it also holds on the closure of it. And for this reason, it holds on this inverse image of xi, on which both guys are defined, because we can take the image of pi only if it suffices to have what I already said. So since this equality holds on the open orbit, it holds identically on here. Okay. Now this means that actually this set x prime, this point x prime, belongs to the open subset xi prime, which we defined as the inverse image of xi under the map pi, because under the map pi, this point gets to x, and x in xi, x is in here. Okay, so this implies I need some more room. I don't have enough room on this page. Maybe I will shift slightly what I have written slightly to the top. Like this. Yeah, I think it is enough. Now I have to shift also these things. Okay, it's perfect now. So my final conclusion is that the point x prime belongs to x I prime. So what we have proved so far, we are proving this claim. So what we have proved so far, we have proved that the image of x double prime under the map pi prime sits in the union of these open subsets. Let me turn now to the next page. So hence, pi prime of x double prime sits in the union of these open subsets xi prime. Because for each point, again, because for each point in x double prime, we proved that its projection, maybe I can write it more explicitly, this x prime is exactly the projection pi prime of x double prime. And we have proved that it belongs to this open subset xi prime for some I.
Hey, Professor.
Yeah.
I mean, you say that the identity holds for x belong to y naught, right?
Yes. And by continuity, it holds on this inverse image of xi.
What continuity? I mean,
this is an equation. This is an equation. So if you write this equation in local coordinates, you obtain some polynomial equations on coordinates of points.
You are talking about this equation, not about x2 prime. Oh, I see.
No, about this equation. But these two points, x prime and x, are components of this point, x double prime. These are two components of this point. This point sits in the product. Yeah. So this is an equation. Finally, this is an equation on coordinates of this point. And if this equation holds on an open subset, it holds on the closure of its subset. This is what I'm claiming. But to make this, so this equation makes sense only on this inverse image because here we map to this xi bar, and we want to have that x, this point x, also belong. So to write this equation, to make sense to this equation, we have this x also belong to this xi bar. So we require that x belongs to xi, because xi bar is not contained in this x, but xi is contained. So this equation makes sense on this open subset by inverse of xi on this open subset, and it holds identically because it holds on the open orbit. This is the argument. Is it okay?
Pi I, the composition of pi I and phi. You mean the composition of pi I and phi is defined on xi, right?
Oh, right. You may say like this.
But I don't think the rational map phi is defined on the whole xi.
Of course, it is not defined on the whole x. Phi is a map.
It can extend to the whole xi since it is locally the open embedding, right?
Well, I mean exactly what I claim. I mean that this map pi prime, about this claim, I mean that this map pi prime embeds x double prime in x prime as an open subset. And the image of this map will be exactly the union of these xi primes.
Well, I don't think we are talking about the same thing. But I understand my question. Thanks.
Okay, that's good. Anyway, even if we were not talking about the same thing, it's good that you understand the answer to your question. But if you still have more questions, then ask me again. Let's continue. We have proved that the image of x double prime under pi prime sits in the union of these open subsets. So let me repeat again that this x prime is contained in the product of xi bars. And I claim that if you take the image of x double prime in x prime, then it will be a subset in here. It will be a subset in here such that for each point in this subset, one of these projections will get into xi without bar, into xi itself. And these open subsets will cover these open subsets xi prime, the subset in here, such that the projection, the ith projection, gets into xi without bar. So these open subsets do not cover the whole x prime, but they cover the image of x double prime under this map, as we have proved here. Now, I claim more. Moreover, I claim that this map pi maps isomorphically pi inverse of xi, which is a subset, an open subset in x double prime, this pi inverse of xi is this subset marked in red. And for different i's, these subsets cover the whole xi bar because xi's cover the whole x. So pi inverse of xi maps isomorphically under pi prime onto xi prime. So let me repeat again that x double prime is covered by these guys, and each of these open subsets isomorphically maps under pi prime onto this guy. Why so? Well, it is clear more or less if you analyze this description written here. Let me write explicitly that if you take any point x double prime in here, then what does this point look like? So this is a point in a product variety. This is a point in a variety, or in this variety x double prime. This is this point in the variety which sits in the product of x and x prime, and x prime itself sits in the product of all xi bars of all these guys. So this point x double prime sits in the product of x and all xi bars, and it has several components. And the components in our previous notation are the following. So the component corresponding to x is just the point small x, which was on the previous page. The component corresponding to xi bar is still the same x, which we have proved here. The component corresponding to xi bar is the ith projection of x prime. So we have x prime and we take this ith projection and we get still the same point x. And of course we have other components, which I just denote by some dots. For instance, we have some point, I don't know how to denote it, say xj belonging to xj bar for some j, and so on. So all these points, all these components give you the point x double bar. And when you take the projection you take the projection to x prime, then you take this point x double bar. Again, let's look here. This x double bar is a pair consisting of x and x prime. And x prime is just the tuple of these components. So all this is x prime. And the projection map pi prime just takes x double prime to x prime. So this means that we just forget this. But you can restore the first component in here from this, because it is the same point. And this gives you that this map is an isomorphism. Okay? Now, since over each of these open covering subsets, the map pi prime is an isomorphism, we finally get that the whole map from x double prime, the map pi prime, from x double prime to this union of open subsets in x prime is an isomorphism. Okay? This proves the claim. We claimed that pi prime embeds x double prime as an open subset into x prime. And here we see what this open subset is. It is this union. And this is an isomorphism onto this open subset. Well, finally, what we can do next, we proved the claim, and now we want to use this claim. How do we use it? So we want to prove that that X is complete. Yeah. So we prove this implication. So we want to prove. So we are given that the fan of X covers the whole valuation cone, and we want to prove that X is complete. So since by assumption, excuse me, since by assumption the valuation cone V is covered by the fan of X, and also by the fans of xi bars for any I, just because these xi bars are projective varieties, and we already proved in the first part of the proof that for a projective variety, for a complete variety, and in particular for a projective variety, its fan covers the valuation cone. This was the first part of our proof. So so the valuation cone is covered by both fans, this one and these fans for any I. And this implies, again, by the properties of elementary embeddings, of elementary varieties, that this implies that for any vector in the valuation cone, there exists a unique morphism from the respective elementary variety. Yeah?
Why the valuation cone covered by... Oh, because xi is open. Oh, I see.
xi bars are projective varieties. And we already proved that if a variety is complete, then it's
projective variety. Ah, I see. Xi bar is the projective variety which we have chosen.
Yeah, exactly. So
but
by
maybe not normal.
Well, you can make it normal. I mean, I didn't say how I choose this projective closure. I can embed this xi in some projective space and then take the closure. But if it occurs to be non-normal, I can normalize. It is not a problem. To normalize, I can always normalize. Okay? So here I can assume that these guys are normal. For any vector in the valuation cone, we get a unique map from the respective elementary variety to X, which extends the identity map on the open orbit, as usual. And for the same reason, we get a unique map from this elementary variety to each of xi bars, yeah, and also to their product, which is x prime. Well, x prime is not their product. X prime sits in the product of xi bars. But if you have a map from the elementary embedding xv to each of these guys, which extends the diagonal map, which extends the identity map on the open orbit, then you get the map to the product variety, and the image will be in here because it will extend the diagonal map. Okay, so you get a unique map from xv also to x prime. And since you get a map to x and to x prime, which extends the identity map on the open orbit, you also get a map to x double prime, sitting in the product of x and x prime. And also a map to x double prime. We get this bunch of maps extending the identity map on the open orbit. And now, for any g orbit, say y, in x prime.
Well, Professor, the map from xv to x, is this map open embedding?
No. It is some blow-down map, I can say. It is not an open embedding. It is only an open embedding on the open orbit. This we can guarantee. It extends the identity map on the open orbit. But generally, this maps the boundary divisor, dv, to some orbit in x, maybe of smaller dimensions. So it is a kind of blow-down map. Okay? So for any g orbit y in x prime, x prime is here, yeah? X prime is this variety. For any g orbit in here, say y, by the blow-up construction, you can find a vector v in the valuation column. So there exists.
Professor, so how is
okay.
How is xv mapped to x prime?
Well, because x prime is a projective variety. Well, no, yes. Well, I mean, because even because we have a map from xv to xi bar, to each of xi bar, and therefore we get a diagonal map.
Xi bar. I was thinking that it only maps to a unique I.
No. For any I, you have this map. Okay? And the diagonal map will take you to x prime. And yet another diagonal map will take you to x double prime. But now for any g orbit y in x prime, there exists a vector in the valuation column such that the respective elementary variety xv maps to x prime in such a way that the boundary divisor dv maps exactly to this orbit y. This xv can be constructed by blowing up y, or the closure of y in x prime, if you like.
Professor, sorry, I mean, you have that xv maps to every xi bar. Yes. So xv is mapped to the product of xi bar. Yes.
Exactly.
But that product is not x prime. So how can we ensure the image is containing y x prime?
Because this map, well, let me write it here. Because this map to the product is a diagonal map. On the open orbit, it is the identity map composed with each projection on xi bar. So it is a kind of diagonal map. For the open orbit, it is just the diagonal map. And also the diagonal image of the open orbit sits in here, because it comes, x prime comes from the image of phi, and phi is again on the open orbit, it is the diagonal map.
Oh, so the two maps coincide because they are the same.
Yeah. Exactly. Absolutely. Okay, so we are close to finishing the proof. So we have this picture. We have, there exists such a vector v, for which the boundary divisor of the elementary embedding maps exactly to the chosen orbit y. But we have already seen that for any v, and for this v in particular, we have a map from xv to x double prime, which agrees with the map to x prime. So this map from xv to x double prime is a diagonal map of these two, of this one and this one. So this means that the image of the composition of this map to x prime, of this map to x double prime, and then the projection onto x prime will give you this map. And this implies that the orbit y is actually contained in the projection under p prime, under pi prime of x double prime. This is this projection from here to here, from here to here. But I mean, what did we prove? What did we prove? We proved that any orbit in x prime is actually contained in the image of x double prime. This means that the image of x double prime just coincides with x prime. So we deduce, let me shift it one line below. We deduce that x, well, let me write it differently. I'm sorry, since I was answering some questions, I went somewhat out of my time, 5 minutes out of my time, but I will finish in a minute. We are very close to the end of the proof. So we conclude that x double prime, which is isomorphic, of course, to its image under pi prime, because our claim says that the projection map pi prime is an open embedding of x double prime to x prime. So x prime, x double prime is isomorphic to its image, but this image actually coincides with x prime, because any orbit in x prime is actually contained in the image of pi prime. And this guy is a projective variety. So we proved that by this isomorphism that x double prime is projective, and therefore, finally, we get that x without primes, just our initial x, which is the image of x double prime under pi, is complete. The image of a projective variety under a morphism is complete. And this ends the proof. So finally, we proved the inverse implication. This ends the proof. We have proved the completeness criterion, and I end this lecture by an exercise to you. Now we know enough to solve this exercise. This is exercise 2. Prove that if you take the cone spanned by all vectors in the valuation cone and all colors, all VD bars where V runs over the valuation cone and D runs over colors, then this cone will be the whole vector space E. Well, this means on the picture that when you take the valuation cone, let me draw for you, what does it mean? This means that when you take the valuation cone, so this is the valuation cone, if you take the valuation cone and the vectors corresponding to all colors, there are finitely many vectors. Yeah. So for instance, I don't know, for instance, this one, maybe this one. Some of colors may sit inside the valuation cone. This also may happen. for instance, this one. If you take all these vectors corresponding to colors, then the cone you get by taking all these vectors, all vectors in the evaluation cone, maybe like this, all vectors in the evaluation cone, and all colors, if you take the cone spanned by all these vectors, then you get the whole vector space. So the colors the vectors corresponding to colors look in somewhat opposite direction. At least some of them look in opposite direction with respect to the vectors of the evaluation cone. This is an exercise for you. And now, finally, I'm stopping now, and you may ask your questions if you still have. Yeah?
Oh, I want to see the last page.
Yeah, let's get to the last page. Just a moment. So.
Oh, I mean, not this. Some another page. Yes, I mean this. I still don't understand why pi prime pi I the value of pi I at x prime is x on every x.
You mean this equation, yeah?
Yes, I mean this equation, because I don't think it is defined on every point in the inverse image of xi.
Well, let me try to explain once more. So, first, you can consider this equation on this inverse image of xi under the map pi on this set, because both sides make sense, and the equality makes sense because
why both sides make sense? I don't think the left side makes sense.
The left side.
Because x prime may not exist.
No, x prime. No, excuse me. X prime always exists because by definition, x double prime is a point on this variety, and this variety sits in the product of x prime and x. So you always can take a projection to x prime.
So we always have a x prime. I see.
Yes, we always have x prime, and we always can project x prime to xi bar, because x prime is a subset in the product of xi bars. So the left-hand side makes sense, and the left-hand side belongs to xi bar. And also the right-hand side makes sense and belongs to xi if we consider the inverse image of xi under the projection pi on this set. On this set, this point x makes sense as the projection onto the first factor, onto here. And it belongs to xi because we consider not the whole x double prime, but only this inverse image.
Oh, so x prime is not the image of x under phi, right? Under little phi.
Well, it can be not defined because phi is a birational map.
Oh, it may be exist just because we take closure.
Well, it is. I mean, so since phi is birational, this point x may not belong to the domain of definition, to the domain where phi is regular.
So this means that there is no point on x double prime that that the image of x double prime is x.
I'm not sure I understood your question. Sorry.
I mean,
your remark.
if phi is not defined at the point x,
Yes. Then
so
you cannot.
then how can we choose a point on x double prime? That is the projection.
This was our initial choice. So what we are doing, we are taking a point on x double prime. This is our initial choice. And you take the projections of this point under pi and under pi prime. So first you choose this point, and then you take its projections.
Yes, we take its projection. So this projection is not surjective, you mean?
Well, actually, the projection is surjective because x prime is projective. X prime is complete. And x double prime is closed in this product. This is a property of complete varieties, that the projection along a complete variety maps closed sets to closed sets.
Yes, I mean, this is a definition of completeness.
Exactly. So this map downwards is surjective from x double prime to x prime. This map pi is surjective.
Is surjective. I still can't deduce why it is surjective. Well, what happens if it is not surjective?
No, excuse me. You just quoted the main property of the complete varieties. The property says that if you take a projection or a product of any variety with a complete one, so
yes.
This is, and
the projection. The projection from their product to the non-projective, not necessarily projected entry, the map is closed. I mean, yes.
It maps closed to closed. This means that the image on the pi is closed, but it is also dense.
Why not, right?
So yes. So the image, it is closed and also dense. Therefore, it is the whole X.
So there must be some X on X prime.
Well, I mean,
there must be some X prime.
For any X in here, you can find some X prime in here, mapping to X, but maybe there are many X primes. So you do not have an inverse map. The inverse map is only rational.
Not have inverse map.
Exactly.
And X double. We take closure to gain X double prime. I see.
Mm-hmm. Yes.
So come back to the identity. Since this is surjective,
when you speak about the identity, you do not need surjectivity. You just consider this as an equation on this set. And I say that this equation holds identically. So both sides of this equality belong to one and the same thing, belong to here, to this.
Belong to xi bar. So
yes.
Both sides.
So we can compare them. This equation makes sense. And I claim that it identically holds.
And it holds on a open dense set, so it is identically hold.
Exactly. This is the reason.
I see.
Well, actually, let me reveal some secret. This argument which I presented is actually the same as the one which proves the Chow lemma. The Chow lemma says that for any algebraic variety, you can construct a quasi-projective algebraic variety and a birational map, a birational proper map from a quasi-projective variety to an initial one. Maybe you know this lemma from algebraic geometry, Chow lemma.
Yes, I've heard of it.
Yes, and actually this argument is taken from the proof of this lemma. I could even avoid the whole proof if I refer to a general theorem due to Nagata. Nagata's theorem says that for any G variety, maybe not complete, you can construct a G equivariant completion of this variety.
G equivariant completion.
Yeah, so any algebraic variety can be completed in a G equivariant way. This is a general theorem due to Nagata. But I didn't want to use this theorem because I can give a proof without relying on this deep theorem. So I prefer to give an explicit proof.
I see.
If we knew the theorem that I can complete my X, then the proof of the reverse implication will be a few lines. Because if I can embed X in a bigger variety, X bar, which is complete, then this X bar would also be spherical, and the fan of X bar would be bigger than the fan of X. But if the fan of X covers the whole V, I cannot construct a bigger fan. This will contradict this property.
I see.
So the proof would be much shorter, but it would rely on a theorem which I could not prove. I preferred not to do this, but give you a more elementary proof, but self-contained. Okay, so are there more questions or comments?
Well, I want to see the next page about the end of the proof.
Okay.
Yes. Thanks.
Any question on this page?
No question.
Good. So thank you for your questions. And on Monday, on the next lecture on Monday, we will consider examples. So now we are finished with a piece of general theory, and it is time to consider examples. The examples will appear on the next lecture, and then we'll further develop theory, geometric theory on spherical varieties on coming lectures by considering examples, particular case, and further properties. So if there are no more questions or comments, I'm stopping sharing the whiteboard. And see you all. I hope to see you all next Monday. Bye-bye.